Thank you for the introduction. So I'm from Japan, and in the traditional storytelling in Japan, an apprentice would give a casual talk to warm up the audience before the master comes in to give the talk. So that's what I'm going to do. So please warm up. So this is the 50th anniversary of the discovery of the gravity in string theory, and Michelangelo Mangano reminded us of this wonderful paper by Shark and Schwartz. But I just wanted to also point out that there was also independent work by Tamiaki Onea that appeared almost simultaneously. And by the way, I am following Juan's example to put these hyperlinks, so you can go to the references. And so Tamiaki Onea was a graduate student in a relatively small university in Hokkaido. And when I was a graduate student, his work was very much inspiring to me. And in this paper by Shark and Schwartz, they have this sentence that says that our analysis suggests that the dual model might perhaps provide a unified theory of electromagnetism, weak interaction, and gravitations. And in some sense, we are still sort of trying to realize this dream that was envisioned in this paper. This is also the 40th anniversary of the first superstring revolution. Michael Green and John Schwartz, anomaly cancellation. David just came in, discovered the heterotic string construction, and a vacuum configuration of superstring where the name Calabi-Yau first appeared in the scientific literature. I was a first-year graduate student when this happened, and I heard a rumor that something great happened at Aspen Center for Physics. But in those days, preprints were shipped on the Pacific, through the Pacific Ocean. So it took 3 months for me to get these papers. So that's very different now. This is also the 30-1st anniversary of the second superstring revolution. And of course, Witten dropped the bombshell on March String 95 conference. And this was followed by D-brane, black hole microstate counting, and ADS-CFT. And in some sense, we are still sort of continue to explore the result, the vision that was displayed by Witten at that time. So does every generation need a revolution, new evolution? This is often attributed to Thomas Jefferson, but this is a misquote. And he actually wrote, the tree of liberty must be refreshed from time to time with the blood of patriots and tyrants. Or are we in the normal science phase where we're setting up stage for the next revolution? As Hideki Yukao said in his autobiography, people who explore the unknown, people like us, are travelers without map. So we don't know whether we are continue to be in the normal stage or going to be the next revolution. But whatever that is, I think we should ask good questions. That's an important first step. And if we have good questions, that can lead to we may not be able to answer that question, but trying to answer these good questions leads us to unexpected discovery and applications. And with that in mind, we have invited people to submit us questions, and we got 100 questions. But we wanted to have questions that can be plausibly answered in the next 10 years. And we have these questions, and these are accessible. At the end of our remarks, we'd like to invite you to first comment on these questions so we can have an interesting conversation based on these questions. We try to actually make these questions clear. Sometimes we receive questions and we try to clarify that and we revise the questions. So I hope these are interesting things to look at, and then I hope we'll have some interesting discussion after our remarks. So I'd like to take this opportunity to make a few comments about some of the questions. And there are lots of interesting questions about the non-perturbative method. She asked, can string theory, field theory be formulated at a fully non-perturbative and quantum level? By the way, again, you can go to the discussion at this link. And when the string field theory was first invented, it looked like a rather awkward and complicated framework to deal with. But for the last 10 years or so, it has been found very useful, and as was demonstrated in Shii's talk, it had many practical applications. And in many cases, it gave rise to results that are free of artifact of renormalization or regularization and gave some unambiguous result, and sometimes much simpler than traditional method. And I hope that this can also give us some insight into non-perturbative method. And in this context, Ashok Sen pointed out that if we knew how to generate a perturbative expansion around all saddle points and also how the desired integration contour is expressed as some of the Lifshitz symbols, we have in principle non-perturbative definition of the theory. Can this idea be applied to string theory? In this context, Nikita has a very interesting suggestion about what are the complex saddles that we might consider having in string perturbation theory. That can non-unitary conformal field theory has a role to play in this context? So these are very interesting questions, but we can also consider applying it to simpler setup. So Riccardo Schiappa, who had developed this idea of resurgence for many years, suggested that maybe it's reachable, doing that can be reachable in a simpler context of matrix model, minimum, and topological string theory. And in this conference, there was actually a beautiful talk by Raghu Mahajan, who developed some of the techniques of how to do the D-brane instanton calculations. And we just heard the beautiful talk by Marcos Marinho, which actually gave me, at least personally for me, a hope that we could plausibly determine the largest behavior of topological string partition function and for compact Calabi-Yau manifold. And being compact is important because that means that you have finite Newton coupling in a non-compact direction. And we can consider matching it to the black hole entropy counting. And that can lead to the unique non-perturbative completion of topological string partition function. And being able to do that can help us gain insight into how to do non-perturbative completion of string theory. But at least within this toy model context, Marcos' talk gave me hope that this is achievable within the next decade. And I haven't worked on this for the last 10 years or so, but I'm very much motivated to come back to this question. So thank you. Space of theories is also a very interesting subject. There are lots of questions about this that was proposed. So I said that this is the 40th anniversary of the first superstring revolution, but there are other interesting things happened. 14 years ago, Dan Freedan got PhD, and his PhD thesis is very interesting. So in this thesis, he suggested an analogy between the classification of quantum field theory and the classification of Riemannian manifold, and proposed this program of understanding the space of quantum field theory. I was a first-year graduate student, and so I said, well, this is like the wonderful vision, but I have no idea how this can possibly be achieved. But in the last 40 years, we have actually learned quite a bit about how this kind of space of theory, what kind of structure? We uncovered lots of beautiful structure in the space of quantum field theory, supersymmetric quantum field theory, conformal field theory, holographic theory, S-matrix, and branes. And there are lots more to be learned in this direction. Sasha Zhivoidov asked, what's the space of holographic conformal field theories? And but he pointed out, well, bootstrap may not be sufficient. And we may need some ingredient. For example, can we exclude a free scalar minimally coupled to general relativity? How do you do that? Well, so here is one possibility of adding constraint. For example, there is a beautiful paper by Asmuth Foxted a couple of years ago, where he actually excluded some of low energy theory in ADS with certain scalar potential using Penrose inequality. This is derived by Engelhardt and Horowitz based on ADS-CFT correspondence. So this is like a clear example where excluding certain low energy theory is possible in this way. Grant Remen asked the corresponding question about S-matrix. Can we prove that string theory is the only consistent perturbative ultraviolet completion of gravity? And there was a very interesting talk, in related talk by Andrea Guerrieri. Did I lose the microphone?
Sounds like it.
Let me see, maybe, or maybe it went out of battery, or did I consume the battery? Okay, so let me try this one. Maybe I spoke too loud. Okay, so I actually wanted to also attract attention to the question about discrete family of conformal field theory. For conformal field theory, if you have continuous family, we still have a lot of things to learn about conformal field theory in continuous family, but we have learned quite a bit of structure of conformal field theory and conformal manifold. But there are lots of interesting questions about the discrete family. For example, in the context of ADS-CFT, especially to take the large n limit or first space limit, we'd like to understand how conformal field theory are distributed as a function of central charge, for example. So one way to introduce structure, understand structure of this discrete family, maybe to introduce the notion of distance between disjoint conformal field theory. And there have been some attempts, but defining distance in a way that satisfies the axiom of distance has been challenging, and I think this is an interesting direction. Classification of branes is also very interesting, and the swampland cobordism conjecture gave us new motivation to explore new types of branes, and we just had a very interesting talk by Kazuya Yonekura about non-supersymmetric brane construction. So there are lots of new things that we can consider learning, we can try to learn in the next 10 years. There seems to be lots of good questions in this area. Swampland. That there seems to be non-trivial constraint on effective theory of gravitational systems. There was a beautiful, well-balanced talk by Miguel Montero on the first day of the conference. The gravity is very different, and many people said that. For example, Cindy Keeler asked, can we develop a mathematically precise measure as to when effective field theory will break down in the context of quantum gravity? And many questions are about how to quantify the prediction of swampland. Can we prove or falsify swampland bound? So Miguel asked a question about global symmetry, and the same question was asked by Julio Para-Martinez. And in this context, the question is that, well, can we estimate how global symmetry can be broken in quantum gravity? And these are important questions. For example, if we want to tell experimenter how long the proton can live, these are important. And Irene asks a corresponding question about the distance conjecture. Okay, so I take my one slide as a speaker to advertise my recent work with Yifan Wang, where we actually achieved some of this quantification that in the distance conjecture we expect that, so in this case delta is a mass, but it decays exponentially in the distance. But in this particular work context of 2D CFT or ADS3, we're able to give both upper and lower bound on this coefficient, which translate into the lower bound by Planck scale. So in the original the original distance conjecture, me and Kamran, we said that alpha is about the order of Planck mass, Planck scale, but we didn't give any numerical value associated to it. But in this work, we are able to actually give precise numerical bound on this case. And I hope there is an opportunity to develop this to higher dimension also, and maybe even in flat space, so that would be very exciting. The jitter space. So despite some of my previous publications, I still remain agnostic about whether string theory allows a semi-stable solution with a positive cosmological constant and with all the moduli fixed. And I hope we'll hear a definite answer to this question in the next 10 years. I'd be very happy if construction is done, and or I would be equally happy if it was proven that it's not possible. I would like to know. And there was actually a beautiful presentation and impressive work by Jacob Moritz presented at this conference. Until recently, there was no single Calabi-Yau construction which combines all the necessary ingredients of KKLT construction. But he was able to achieve that, and that's a wonderful thing. There are still challenges like how to control alpha prime corrections or large two-hoof coupling. But I think it's important to settle the question of whether KKLT construction can be realized in string theory, and the talk by Jacob gave me hope that this is achievable in the next 10 years. And Jacob himself asked this very interesting question. the success, if you succeed in making such construction, you can ask lots of interesting questions, like, can you explain Dojita entropy, or can you, does it give you macroscopic interpretation of Dojita entropy? In the first formulation of Jakob's question, he didn't have this word such as KKLT. I guess he's too modest. So I didn't quite understand what microscopic construction of Dojita cosmology means. So I asked him for clarification, and he kindly agreed to insert this word, such as KKLT. So now I understand what he meant. I have one more wish, and this is very personal to me, which is proposed by Greg Moore. Is there a conceptual explanation of mushroom moonshine, including genus zero phenomena? Can we understand mushroom moonshine? Well, Greg said that good people have tried hard for the last 14 years, and we are still waiting for the aha moment. So if the answer is yes, probably a new idea is required. I think this 14 years refers to my paper with Toru Eguchi and Yuji Tachikawa, but I would like to point out that this paper was trying to interpret my PhD thesis, which was 35 years ago, that there I calculated the expansion of elliptic genus in terms of Mach zeta function, had found a bunch of integers. And it took us 21 years to understand that these are dimensions of Massieu group M24. So I do hope that in the next 10 years, there will be another aha moment where we finally understand what this Massieu moonshine means. And there are many more interesting questions and helpful hints. And I hope we'll have a very interesting comment from the audience about some of these questions. So this is the 50th anniversary of the discovery of the gravity in string theory. So I asked John Schwartz, my colleague at Caltech, how he feels about it. And he said that I'm pleased that after 50 years later, it is still plausible that string theory can provide a realistic quantum theory of gravity and other forces, which goes back to the sentence that I quoted in the first slide. And in fact, for the last 50 years or so, string theory has made remarkable achievements already, that it is a consistent quantum theory of gravity, and there is no other game in town. And being so, it provides a basis for theoretical speculation about gravity. So there are, of course, nowadays many works which does not directly refer to string theory, but string theory gives a theoretical basis of those speculations. Otherwise, we might be considering discussing some empty set. So this is very important. And it contains all the ingredients to construct the standard model of particle physics. And it contains a promising candidate for the dark matter, and may be able to explain the dark energy, and provide guidance for future experiment and observation as alternative to naturalness, and provide new insight and a powerful tool for studying quantum field theory, and also inspire progress in mathematics. So I think we're going to have a wonderful 10 years from now, and I'm very much looking forward to. I wanted to thank the organizer at the beginning of the presentation, but David just walked out. So I'd like to first thank the organizer, but I would also like to thank David for ensuring that this wonderful series of conference continues. So thank you very much.